Hello everyone, this is Zhuoping and I'm very glad to present our work, AGILE, lightweight and efficient asynchronous GPU-SD integration. This is a joint work between Brown University and Syracuse University. Nowadays, general-purpose GPU are the main engine behind modern applications such as deep learning, computer vision, autonomous driving, graph analytics, video processing, scientific simulation, or finance or risk modeling, and especially AI applications, and they are really now reshaping the world. If we take a look at specific AI applications, assume that we are now browsing some online shop, and as a user, we want to see more items that we are interested in. And also, the online shop provider may give us some items that we want to buy. To achieve this goal, we can use some recommendation system, and which will take in some users information and also the items information, which will generate how likely a user will click on this item. By doing so, we can create a list that the users may be interested on all the items. If we take a look at the recommendation system, we can see that there are two MLPs, which are computationally intensive, and we can use GPU to handle these tasks efficiently. And we can also have another task, which is called embedding table lookup. And in this process, the recommendation system needs to deal with a huge amount of data, and the huge embedding tables are far beyond the GPU memory capacity, and also its irregular access. And in this case, we can say that modern applications are more than just computation, and we also need to handle a huge amount of memory footprint. But nowadays, the GPUs are increasingly constrained by the memory war. And if we take a look at this figure, which shows the trend of how memory capacity increases for GPU and how AI model increases. And every 2 years, the GPU's memory only increased by 2x. But for transformer model size, it increased over 400x every 2 years, which means that we cannot use a single GPU to handle this kind of large models effectively. But if we take a look at the modern computing system, we can find this hierarchical memory pyramid. And on the top of this pyramid, we can have a GPU memory. And for the latest Blackwell B200 GPU, a single GPU can provide us 192 GB memory. And in the system DRAM can scale to a few hundred gigabytes, or for some high-end system, we can have 2 terabytes memory, which is still not enough for the large models. But for SD system, we can easily scale it to petabytes level. And I did a quick check. If we buy a Micron latest SD, a single SD can provide us more than 200 terabytes storage. So in terms of capacity or cost effective, the SSDs are really a good candidate for hosting this kind of large models. If we use the largest models in this figure, which is from Baidu's recommendation system, we can use a GPU-only solution and one GPU plus several SD solution. And I did a quick calculation. For the GPU-only solution, we need to pay $515,000. But for one GPU and the full SD solution, we only need to pay $36,000, which is 14x cheaper. So which is really good. But the bad thing is that the SD storage is slow and the bandwidth is also low, which means that we need to apply more techniques to optimize it so that the GPU can leverage the large storage space from the SD efficiently. And the existing the SOTA work ban propose a GPU-centric access model. In this model, the GPU can issue some command to the SD directly, and then the SD can send the data directly to the GPU as well. In this process, the CPU is bypassed completely in both the control plane and the data plane, and which means that there is no extra data copies and there is no overhead, no synchronous overhead between the CPU and the GPU, which is pretty good. And also, the band provided us a super cache mechanism, which we can cache some hot data on the GPU memory, and we do not need to fetch data each time from the SD, which is pretty good. And this system is a really effective system for GPU to use SSDs. But how can we further improve the GPU-centric storage access model? And we can take a look at the programming model for GPU-centric I/O. For BAM, it adopts a synchronous I/O model, which means that when we call this read block function, it's a block read, and the function will return only after the slow transfer is finished. And the GPU threads must wait for the slow transfer. But if we have an asynchronous I/O model, and when we call this read asynchronous, it will just issue a request so that the function can be returned immediately after the request is issued. And at this time, we can switch to other tasks in order to hide the high latency from the slow disks. And later, we can resume the computation once the data is ready. So in this example, we can say that the asynchronous I/O enable overlapping between the slow transfers with other tasks, which is really good. But how can we support this kind of asynchronous GPU-centric storage access model efficiently? The answer is use AGILE, which is proposed by this work. Before jumping into the detail of AGILE system, we can take a look at the NVMe protocol. Assume we have a CPU and an SD, which are connected by the PCIe interface. And on the CPU, we run a host program, which we are going to read some data from the SD. At the beginning, we need to allocate some contiguous buffer inside the memory and submit a command based on the contiguous buffer to the completion queue or SQ inside the host program's memory. And then we need to ring the doorbell register inside the SD so that the SD will know there is a new command available so that the SD can fetch the command and then using its DMA engine to do the data transfer to fill the allocated buffer. And after the transfer is finished, the SD will send a completion message to the completion queue or CQ on the host program. And later, the host program can check the completion message in the CQ to release some entry in the SQ and know that the data is ready in the allocated buffer. And in this case, we can say that the NVMe protocol is fundamentally asynchronous, but when it comes with GPU, the thing is challenging because the GPU has a lot of parallel threads, and each of these threads can issue multiple requests, but the IO queues are relatively limited. So this can lead to a deadlock problem. And this example shows how deadlock happens. So assume we have one SQ and the other entries are occupied by other threads, and we have two available entries in this case. And now we have two threads, and these two threads want to execute this pseudocode. And at the beginning, both threads can reach to line 2, and they can successfully submit their command to the SQ. And now the SQ is fully occupied. And when these two threads goes to line 3, they want to submit another command, but there is no available entries for them to use. Therefore, they have to consistently checking here. So these two threads are blocked here, which means that they cannot reach to line 5, where they can process the completion message and release the corresponding SQ entries for other threads to use. So this will cause a deadlock. If we take a closer look of the reasons for the deadlock, we can find that the root cause of this deadlock is allowing user threads to hold multiple locks that can block other user threads, which is quite common in IO queues and also in the software cache lines, and I will explain these two parts later. For IO queues, we provide some Agile pooling service to avoid the deadlock. The figure still shows the two threads are blocking at line 3. But if we have Agile pooling service, which we are consistently checking the CQ to see if there is a new completion message ready. And in this case, during the two threads blocking at line 3, the data for thread 1 is ready, and the pooling service will know because it's consistently checking the CQ. And then the pooling service can release the corresponding entry so that there is another new available entries in the CQ, in the SQ. And one thread can submit their sequence command to the SQ. Similarly, when another data is ready, the thread 2 can submit another command as well, so that both threads can continue to execute without being blocked by others. In this way, we can solve the deadlock problem. And to eliminate the deadlock problem from the server cache, Agile does not allow user threads to avoid cache line eviction. Here is an example shows how Agile works in this case. Assuming other cache lines are occupied by other threads, and we have two available lines in this case, and we have one thread which go into line 2, and uh, uh, it will request a new cache line and issue some data movement. And it goes to line 3, and it will request another cache line, and it generates a new command, and goes to line 4, where it can do other tasks. And during this time, data A is ready, and later the program can pass the barrier function at line 5 easily because the data A is already ready. And when it goes to line 6, when it waits for data B, but at this time, other threads may request new server cache lines, and we have to kick out some cache lines in order to avoid deadlock. And in this case, we can find that A is ready, but no one are using it now, so that we can evict A to avoid blocking others. So at this time, B is ready and we can move forward. And at line 7, we need to use A and B for some computational tasks. But at this time, A is unavailable again. So in this case, Agile will use an extra synchronous rate to load A when the users want to access A. So in this way, we can avoid blocking other threads and eliminate the deadlock problem. But we have to pay some additional IOs in this case. So because by default, all accesses are proxied by Agile Server Cache and the request data may be unavailable again because we need to eliminate the deadlock, which is not really good. To address this problem, Agile allows users to integrate some user-managed buffers to Agile's Server Cache hierarchy. And all things users need to do is to declare some user-managed buffer and use some asynchronous API provided by Agile, and then wait on this buffer. And the data in the user-managed buffer will not be evicted by the Agile framework, so that later the data is guaranteed to be ready when the users want to do computation. So this is good. But another problem is that this can lead to some data conflict problem. And in this case, thread 1 and thread 2 are using the same pieces of data, and both of these two threads obtain a copy of this data. And these threads do a partial update to the copy. And then these threads want to update this copy to the global server cache. But at this time, the data conflict happens. So to avoid this problem, Agile provides a compile time optional mechanism, which is called share table. The share table will allow users threads to access the same user managed buffer, so that we can avoid this data conflict problem. And when the share table is enabled at the compile time, the user managed buffer can be viewed as a L1 memory, which is managed by user, and users need to register it to the share table. And the software cache in the HBM can be viewed as a L2 memory, which is managed by AGILE. And the SSDs can be viewed as a L3 memory, which is managed by AGILE as well. And we also want to provide some easy to use API for users. And in the CUDA kernel, users can use the prefetch API, which will load the SSDs to the server cache asynchronously, and also they can use the asynchronous issue API, which allows users to do asynchronous data movements among the user managed buffer, the software cache, and also the SD. And also, you can use Agile in the synchronous mode. And Agile provides an array-like API. In this API, you can view the SDs as a two-dimensional array. And Agile also allow users to customize their own software cache policy by implement a new GPU cache class. And because users need to handle some locks in when they customizing the software cache policy, we provide a debug option to detect the deadlock for users. So if this debug option is enabled, the Agile framework will track the dependence of the locks. And if Agile finds some locks are interdependent, which means a deadlock happens, so that Agile can report to users and let the users know which locks are interdependent. So the CPU's program is also very simple. The users only need to initialize Agile and start the Agile service and call the user kernel. And once the user kernel is ready, and you just need to stop the Agile service and close as this. So it's very simple. And here is a summary of Agile system. We have CPU, GPU, and SSDs. And on the CPU side, we have some IO queues, which will allocate some IO queues on the HBM and establish the peer-to-peer communication between the SSD and the GPU. And on the GPU part, users can write their own CUDA code and interact with Agile's control API, which provides users the GPU-centric asynchronous I/O model, and we also eliminate the deadlock risks in asynchronous NVMe I/O via the lightweight Agile pooling service. And we also allow users to customize their software cache policies, and we also allow users to integrate some user-managed buffers to the software cache hierarchy. To evaluate Agile, we use a dial server, and on the dial server, we install an NVIDIA RTX 5000 ADA GPU, and we also have one Dell SSD and two Samsung SSDs. And for the software cache policy, we keep the same software cache policy with BAM. And at the beginning, we evaluate the effectiveness of overlapping between the computation and the communication. We use one thread block to issue 64 commands and use the fetch data for computation. And we sweep the computation-to-communication ratio from 0 to 2. And in this experiment, we can see that the Agile asynchronous mode achieve a very similar performance with the ideal case. And in the ideal case, we assume that the computation and the communication can be overlapped perfectly. And this shows that we can enable this overlapping effectively. And then we evaluate Agile using the 4K random read and write to see the scalability of Agile. And we access different SSDs in an interleaving fashion. And we can see that Agile has good scalability in both read and write. We further evaluate Agile on some deep learning recommendation model inference macro benchmark, and we compare Agile with BAM. And we use cuBLATs for all matrix multiplications, and we only use Agile and BAM for fetching data. And Agile is configured in both synchronous mode and asynchronous mode. And we sweep some key parameters in the DLRM inference macro benchmark. First, we sweep the batch size from 1 to 2K. And in this case, we can see that Agile synchronous mode always outperforms BAM, and Agile asynchronous one always outperforms Agile synchronous one. And we also sweep the number of LQs, and also Agile synchronous mode always outperforms SPAN. And for Agile synchronous one, it first achieved a similar performance with the Agile synchronous one. This is because when the LQ is limited, the Agile asynchronous mode will downgrade it to a synchronous mode automatically. But if we scale the number of LQs further, the Agile asynchronous mode will always outperform Agile synchronous mode. And we also sweep the software cache size from 1 megabyte to 2 gigabytes. And we can still say that the Agile synchronous mode will always outperform BAM, which shows that Agile is very efficient even if we use Agile in a synchronous mode. But for the asynchronous mode of Agile, it first lag behind. This is because the software cache size is very small, and we have to kick out some data even if this data is just fetched and haven't been used. This is necessary because we need to avoid blocking other threads to eliminate the deadlock risks. And if we scale the software cache size to a certain point, such as 64 megabytes in this case, the Agile asynchronous mode will always outperform Agile synchronous one again. Thanks for listening. I'm very happy to take any questions. Agile is open source, and please check our GitHub repo. Thanks, everyone.